Good afternoon. My name is Kobe Wordlaw, and this is the Lab 5 introduction. In this lab, we will collect observational data of a magnet falling through a conductive tube of aluminum foil, model the magnet tube interaction computationally, and then compare the computational and observational data. So for this experiment, you're going to need the following materials: an aluminum foil roll, a meter stick, a bar magnet, and your smartphone. To start, you're going to need to find which side of the bar magnet is North Pole. Next, you're going to get the aluminum foil roll in the frame of the video. I actually added my laptop into this and put a stopwatch on it to make it kind of easier, and I just went frame by frame after videoing it. So you're going to set up the aluminum foil roll and drop the bar magnet down the center of the tube while videoing it. And then once you get the video, you're going to go through frame by frame and pick out the times when it enters and when it exits. You're going to do this 5 times and then collect the average time that it took for the bar magnet to fall fully through the aluminum foil roll. So now moving on to the code. We were actually giving a starter code for this lab, and it was laid out in steps. So I broke this down for you guys to further explain them. Starting with step 1, we were told to set up our initial conditions, including the geometry of our tube and the magnetic moment of our bar magnet. So this is why you needed the ruler. It was to measure the length of the tube, the width of the foil, the inner radius of the tube, and then we can use those to calculate the actual radius from the center to the outer surface. This is where some of my error came into play, because I didn't notice afterwards that we needed an aluminum foil thickness of minimum 1 centimeter, and mine was smaller than that. So in the computational model, I went ahead and inputted that 1 centimeter and just made it exactly 1 centimeter instead of my actual measurements. But everything else is accurate to my actual experiment. And then moving on to the second part of part 1 is where we needed the magnitude of the magnetic dipole moment. And I took this from lab 3, as well as the equation to calculate the what was it called? The magnetic field relative to a bar magnet. So, as the magnet falls, we know that the flux is changing in time. Therefore, we needed to calculate the rate of change in the magnetic flux through each ring. So we have the equation for calculating the flux with respect to time, and that is 3 over 2 times mu naught times the dipole moment, the magnitude of the dipole moment from the magnet, times the distance between that magnet and the aluminum foil, then the velocity of the magnet times the radius of the foil over the radius squared plus the distance between the magnet and aluminum foil squared to the 5/2. And this is inserted into our code below between lines 103 and 110. And you can see where we calculate the radius ring, then the distance, which is the magnet position minus the ring position. Then we have the speed, which is the magnitude of the bar magnet's velocity. And then we kind of separated that equation above into a numerator and a denominator, and then basically calculated that where it says df dt, which is the time derivative of magnetic flux over time. So next up is steps 4, 5, 6, and 7, which is use Faraday's law to calculate the current induced in each ring by the falling magnet. Use the Biot-Savart law to calculate the force exerted on each current carrying ring by the falling magnet. Use Newton's third law to calculate the force exerted on the falling magnet by the whole tube on the current carrying rings, and to calculate the net force on the magnet by including gravity. So we can find the current by knowing R and EMF, which is resistance, and the EMF. And we just calculated the EMF in the previous slide, which was the time derivative of the flux. So next, we know that force is going to be equal to that current times delta L times the magnetic field of the magnet. And we can actually replace delta L with the circumference of the loop, because we're only calculating that y component because the x and z components are going to cancel out, which is going to take me into this next explaining. So because that x and z cancel out and we only need the y component, we know that the magnetic field from the magnet makes an angle of theta. So the force is going to be 90 minus that theta. So that is going to give us force sine theta, where sine theta is going to be the magnitude of the cross products between the dipole moment of the magnet and the magnetic field, which is listed at lines 161 through 165. So that is where we have the sine theta, which is the cross of the dipole moment and the magnetic field. And then the circumference, which is 2 pi times the ring radius. And then the magnetic force on the ring. the force on the ring, the magnitude of that. So that whole equation that I just explained is going to be on line 165. But then we also need the force of gravity, which is going to be mass times the gravitational constant. And then we can take the force on the ring and then add that to the force on the magnet to get the magnetic force. Then we can add the magnetic force and the gravitational force to get the net force. Lastly is step 8, which is use Newton's second law to write position and velocity, updating code to model the motion of the falling magnet. We know that Newton's second law states the acceleration of an object as produced by a net force is directly proportional to the magnitude of the net force in the same direction as the net force and inversely proportional to the mass of the object. So therefore we got the equations velocity final is going to be equal to velocity initial plus the net force over the mass times delta t. And once we have that final velocity, we can find the final position, which is going to be equal to initial position plus the final velocity times delta t. And then we input that into our code in lines 179 through 180. And then we can run our code. So here are the results. My coded data gave me 1.642 seconds, which is different from my experimental, which was 0.574. But I stated before, this is different because my experimental data had a thickness that was less than 1 centimeter for the aluminum foil, but my coded data, I actually inputted that 1 centimeter to make it more aligned with my assignment. So, what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? The dynamics of the falling magnet would change because our force is going to be negligible from the aluminum foil. This is because the current is going to be 0, because current is equal to EMF over R, and if R is 0, then our current is not, we don't have a current. Therefore, our force from the aluminum foil, which is I times delta L times B, is going to equal 0 because our current is 0. Therefore, we would only need the gravitational force. Second question is, what if the holes or slots were cut into the tube? How will this affect the ring currents in your model? This would affect the current throughout the model, basically. So we would have a different current at different times. It wouldn't be a constant current. And that concludes my lab.